So, a quick summary of what we've learned. Let's compare magnetic and electric fields. Firstly, the direction of the force. For electric fields, the force will be along the direction of the field, either in the same direction or the opposite direction. But for magnetic fields, the force is perpendicular to the field lines. Secondly, the motion. Now, the electric force acts whether the particle is moving or not, but magnetic force only acts when a particle is moving, and the faster it is moving, the stronger the force will be. And thirdly, the work. The electric force does work in displacing a charged particle or changing its speed. But the magnetic force does no work since it acts at right angles to the motion, and so the FDS, which you'll remember is the expression for work, is zero. So the particle's kinetic energy is not changed. The force is only deflecting it, not speeding it up or slowing it down. You'll be familiar with the name of J.J. Thomson, who's best known in junior science for proposing the plum pudding model of the atom. He did that after his discovery of the electron, which was the first evidence that Dalton's solid atom model was wrong and that atoms in fact were made up of smaller particles. Scientists had discovered that electric current would travel through a vacuum tube in a stream of what they called cathode rays. They didn't know what these rays were, but various experiments were done on them, culminating with Thomson's use of crossed fields to find the ratio of the charge to the mass of these rays. So he's credited with the discovery of the electron, the first subatomic particle to be discovered. And the way that he did it was essentially what you saw in the demonstration. The electrons moved along the tube, the electric field deflected them one way, and the magnetic field deflected them the other. When the field strengths were just right, the electrons were undeflected, showing that the forces were balanced. So we're going to work through his calculations. So let's look at what Thomson was doing. We start with an electron heading in this direction at a speed v. Now, there was an electric field, and we'll say that it was moving downwards so that the electron will be deflected towards the positive plate in the downwards direction. At the same time, though, there was a magnetic field which would have been counteracting the effect of the electric field. So let's think what direction that would have to be acting. Now, I find the easiest way to do it is to think that the force on an electron moving to the right would be the same as the force on a positive charge moving to the left. So I point my thumb to the left, and I need to have my palm pushing upwards, which means towards that negative plate. So if I do that, I have my fingers, in fact, pointing out of the screen towards me. So we have a magnetic field here. So what we really care about is the sizes of them, though. So step one in Thomson's process was to balance the force from the electric field to make it equal to the magnetic field. Now, there's an expression for each of these. That is EQ, and this is B times Q times V. Q's cancel. What we're left with is not a final answer, but just a way of working out the speed of the electrons. Now, that doesn't seem much, but we know what the electric field is, and he knew what the strength of the magnetic field as well. So now he knew the speed. Now, step two is that you turn the electric field off, but you keep the magnetic field the same. Now that you only have a magnetic field acting, the electron will go in a circular path, and the magnetic force is providing the centripetal force that keeps it in the circle. So we have B times Q times V equals mv squared over r. Now, one of the v's cancels out. We want to end up with Q divided by m, because that is the charge to mass ratio of the cathode ray, which we now know is an electron. So if I have Q over m, I've taken the m over to the left-hand side. I need to divide by B, and I have V at the top here. But I'm going to substitute in my expression for V, so I end up with E over B squared times R. Now, R, he was able to measure, looking at the deflection and measuring the distance and using geometry. So he got that. The B field was known. He was using things called Helmholtz coils that I will show you a picture of later. And of course, the electric field was known because he knew the voltage and the voltage across the plates and the distance d between them. So that let him come up with a value for the charge to mass ratio of one particle that made up the cathode ray. And it turned out, in fact, to be 1.76 by 10 to the 11 coulombs per kilogram. He didn't get that exact value. This is the current value that we have. But knowing the size of the charge to mass ratio for atoms, he was able to see that this particle was in a completely different category altogether.